Okay, at this point we know these three formulas. If you need to take a minute to write those in your note cards, you can. Input work is equal to effort distance times effort displacement, or the displacement that the displacement of the effort force. Output work is equal to the resistance force times the distance that the resistance moves. And remember, you can never get out of a machine more than you put into it, so input work has to be greater than output work. So we're going to talk now about these words: efficiency, mechanical advantage, ideal mechanical advantage, actual effort force, and ideal effort force. Talk to you guys about what they are, and I'm going to do that using an incline plane or a ramp, okay? Now, before I do that, though, I want to remind you, remember, we use machines for two reasons. One, to change the direction of our force, such as a pulley. When we pull down on a pulley, the object moves up. We also use machines to change the amount of force required to do work. So let me show you what that means using an incline plane, okay? So you can imagine here that we have this box, or this object. Let's say that it has a mass of 50 kilograms. So at this point, I hope that you know, you can calculate the weight of this, the gravitational force. Let me grab my calculator. So the weight of this box, remember to find weight, it's just mass times gravity, so 50 times 9.8. And so 490, that's the weight of this box, 490 newtons, okay? And I'm gonna use this incline plane. Let me try to get closer. I'm gonna use this incline plane to lift this box 3 meters, okay? And I'm gonna use a ramp, and let's make the ramp 10 meters long, okay? And I'm gonna push the box up the ramp, right? And so I'm gonna push with a force of, let me get one I want. I'm gonna push with a force of 245 newtons. Okay, so here we are in this situation. I have this 50 kilogram box. I want to get the box 3 meters off the ground. Obviously I can pick the box up if I wanted to, but I don't want to do that. I want to use an incline plane. The incline plane's 10 meters long, and I'm going to push with a force of 245 newtons, okay? And so why am I using this machine? Well, if I didn't have a machine, if I wanted to simply take this box and lift it straight up, how much force would I have to apply if I wanted to lift the box straight up? You should know from last week, if I want to lift something straight up, the force that I have to apply has to be the weight of the object. So if I were taking this box and lifting it straight up, I would have to apply a force of 490 newtons. I would have to pick it up 490 newtons, and I'd have to lift it 3 meters. That's what I would have to do if I had no machine. However, I do have a machine. I have an incline plane. And so instead of needing to apply 490 newtons of force to lift it, all I'm going to do is push with 245 newtons of force. So what's the benefit of using this ramp? The benefit of using this ramp is, instead of applying 490 newtons of force, I only have to apply 245 newtons of force, okay? All right, again, I'm talking about these 4 words, 5 words: efficiency, mechanical advantage, ideal mechanical advantage, actual effort force, and ideal effort force. So let me talk to you about what those things mean using this example. Again, remember, if I didn't have a machine, I would have to apply 490 newtons of force to lift this box. However, because I'm using a machine, I only have to push with 245 newtons of force, okay? So the benefit to using this machine is I'm applying 245 newtons rather than 490 newtons. Now, if I didn't use the machine, I would only have to lift 3 meters. But because I'm using the machine, I actually have to push 10 meters, but I'm just pushing with less force than I would need, okay? So now, before I talk about the 5 words, I want to show you guys how to calculate the input work and the output work, okay? So input work is the effort force, we think of it as the applied force, times however far I am pushing. So 245, this is my applied force, or in this case, that's my effort force. That's how hard I'm pushing. And I'm pushing it how far? I'm pushing it over this distance, a 10 meter distance. So that's the displacement of my effort force. So to calculate my work input, it's actually very simple. Effort force times effort displacement, 245 times 10, 2,450. Remember, work is calculated in joules. So I don't know if you guys can see that. Let me back up a little bit. There we go. So again, 245 times 10, 2450 joules. That's my input work. The output work, remember, work is just force times displacement. So it's still force times displacement. It's just instead of the effort, I'm looking at the resistance. And so remember, I said earlier, the work output is like, why did I come to work today? What's the purpose of me being here? I came to work today to lift this box. I needed to lift this box 3 meters. So those are the numbers that I'm going to use to calculate my output work. Don't use 50 kilograms. Kilograms is mass. Work calls for force. So the weight of this box is 490 newtons. This is actually the resistance force. It's the force that I need to apply to move the resistance or to move the object. So my FR is 490. How far am I lifting this box? I want this box to lift 3 meters off the ground.
Teacher, pardon this interruption.
So I want to lift this box 3 meters. That's the displacement of the resistance. I want to get it from here up to here. Now, obviously, I know I actually move at 10, but what's the purpose of the machine? Why did I use the machine? I used the machine to lift this box 3 meters. That's why I was hired. So to find the output work, it's just simply the resistance force times the resistance distance. I can't do 490 times 3 in my head. It's 1470, so 1,470 joules. That's the output work. So what does that mean? That means that I applied 2,450 joules of work to the machine. The machine in turn did 1,470 joules of work for me, okay? So remember earlier I said your input work always has to be bigger than your output work. You can never get more out of a machine than you put into it. So you can see here that that's true. Okay, so now that we've done that, let's talk a little bit about these other words: efficiency, mechanical advantage, ideal mechanical advantage, and then the 2 types of effort forces. So efficiency is just exactly what it sounds like. How efficient is this machine? How close to perfect is this machine? So we know, like a perfect machine, if we had a perfect machine, something that would be considered perfect would be something with absolutely no friction. There are no perfect machines in real life, nothing at all. For this class, we're going to pretend sometimes that they're perfect and sometimes that they're not. But if I had a perfect machine, no friction, no heat loss, nothing. If I had a perfect machine, it would be 100% efficient. Okay? If I had a perfect machine, it would be 100% efficient. If the machine was perfect, if it was 100% efficient, that would mean the input work and the output work would be exactly the same. Whatever I put into the machine, I didn't lose any work due to friction. I didn't lose any work due to like heat loss or anything like that. So these two would be equal. The input work would be equal to the output work. We know there are no perfect machines. There is nothing that's 100% efficient. But what we can do is use the amount of input work we have and the amount of output work that we have to decide how efficient our machine is. And it's actually very simple. To calculate efficiency, I'm going to erase this. To calculate efficiency, it's a percentage. All you have to do to calculate efficiency is to take the output work, the work that the machine puts out, divide it by the input work, the amount of work that you put in, and change it to a percentage. That's all there is to it. It's very simple. So efficiency for this machine, the machine put out 1,470 joules of work. I put in 2,450 joules of work. So for this particular machine, again, all you do, it's very simple. You just divide 1,470 divided by 2,450. My calculator, you can see, says 0.6, but you need to put it as a percentage. So that's 60%. So this machine is not very efficient. It's only 60% efficient. The reason that it's not so efficient is there's probably a lot of friction on this ramp. And so there's a lot of work lost due to friction. So efficiency, it's just a measure of how perfect the machine is. It's calculated output divided by input, and then you express it as a percentage. This machine is not very efficient. It's only 60% efficient, which means it's lost like 40% of its work because of friction or heat loss or something like that. That's efficiency, okay? And so that brings me to the next 2 words, mechanical advantage and ideal mechanical advantage. So I'm gonna erase this and look back at our problem. And so here's the definition of mechanical advantage. You ready? The definition of mechanical advantage, it's how much a machine multiplies your effort force. How much a machine multiplies your effort force. That's a definition. Mechanical advantage, how much a machine multiplies your effort force. And the ideal mechanical advantage is how much a perfect machine multiplies your effort force. So that's the only difference in the two. Mechanical advantage, how much a machine multiplies your effort force. Ideal mechanical advantage, how much a perfect machine multiplies your effort force. So how do I use those in terms of machines? So let me show you guys, all right? Going back to the example of this, moving this box up the ramp, okay? We already decided earlier, if I had no machine at all, how much force would I have to apply to lift this box? If I had no machine, I would have to apply 490 newtons of force to lift it, because that's the weight of the box, if I had no machine. However, I have a machine. Thank goodness. What kind of a machine do I have? I have an inclined plane. Because I'm using this machine, I don't have to put in I don't have to apply 490 newtons of force. I only have to apply 245 newtons of force. So with the machine, I'm only applying 245 newtons of force. So did this machine help me? Yes, it helped me. It allowed me to use less force than if I didn't have the machine. So is there an advantage to using the machine? Yes, there's an advantage to using the machine. That's called the mechanical advantage. Here's how you calculate the mechanical advantage. It's very simple. This number, 245, divided by this number, 490. And so 245, let me get my calculator, 245, y'all, I did that backwards, I apologize. 490 on top, divided by 245. So 490 divided by 245, according to my calculator, is 2. So the mechanical advantage of this machine is 2. There's no unit. It's just simply a number. There's no unit at all. How did I calculate it? 490, that's the resistance force divided by the effort force. So this is the formula for mechanical advantage, okay? And so let me remind you the definition of mechanical advantage. The mechanical advantage is how much a machine multiplies your effort force. So what does that mean? Well, looking at this, what was my effort force? My effort force was 245. By using this inclined plane, I'm multiplying my effort force by 2. So 245 times 2 is 490. It's telling me that I can lift something, with this machine, I can lift something that weighs 490 newtons. Let me show you another example. Like, let's just say, for example, you are applying a force. Remember, we call our applied force effort force now. Let's say that you were using a machine that allowed you, and you were only going to apply 100 newtons of force. Let's say that this machine had a mechanical advantage of 4. So I might ask, for instance, if you're applying a force of 100 newtons to a machine that has a mechanical advantage of 4, how much weight could you lift? So the definition of mechanical advantage, it's how much a machine multiplies your effort force. My effort force is 100, my mechanical advantage is 4, so how much can this machine multiply my effort force? It can multiply my effort force by 4, which means I can lift something that has a weight of 100 times 4. I can lift something that has a weight of 400 newtons. That's what mechanical advantage is.